So, today we are going to look at three different technologies like high pressure processing, pulse electric field processing and food radiation. These three technologies are non-thermal technologies. So, I think we will kind of discuss what are the principles behind them and the equipment and their applications. So, what is the reason these technologies kind of come into picture? Traditionally we have been doing thermal processing more than 100 years or plus. Historically we have been cooking food. So, why there's an interest in non-thermal processing technologies? While heat processing can make the food safe, the quality can be degraded with the heat processing, especially during canning. Volumetric technologies such as heating, microwave heating, they can able to minimize that degradation. Still, you have to heat that material to higher temperatures, and then the cooling of those, once you reach 121, there's going to be a lot of slow process, conduction, convection process. As a result, the food processors are interested in looking at technologies that can preserve food in a different way, and the non-thermal technologies kind of provide answer. In addition, the last 2 decades there's more interest from consumers, safe foods, healthy nutritious food, no preservatives and things of that nature. You can approach this in multiple different ways. One is try to develop processing oriented technologies. The second is ingredient technologies. Like I think again there's a lot of ingredients being used which are synthetic in nature, but now they are replacing them with the more natural ingredients, natural antimicrobial compounds, which has a similar functionality. And at the end of the thing, once everything is done, you're probably going to have a combination of processing technologies and ingredient technologies where you can able to accomplish some of the goals of the process. Now, the note, there's a lot talk about clean label products, but at least from the US point of view, there is no legal definition for clean label. This is a term kind of used in the common people as well as trade magazines, things of that nature, but there are no legal definition for that. So, what is non-thermal technologies? Non-thermal technologies use a lethal agent other than heat to inactivate microorganisms without destroying the nutrients. This may be used at very high pressures, electric field, UV, ultrasound, cold plasma, and generally non-thermal technologies at room temperature do pasteurization effect. Remember yesterday or like during the past lectures, we talked about pasteurization means inactivation of vegetative form of bacteria, but spores survive, so it requires refrigeration storage. So, most of the non-thermal processed food currently in commercial practice, you have to keep them in refrigeration. Now, one of the other interesting limitation for non-thermal technologies is they are variable efficacy with enzymes. So, in other words, not all the enzymes inactivated while you are inactivating vegetative bacteria. So, you have to consider that as well. Oftentimes, a simple blanching technique with the heat may be a good enough to take care of enzymes before you use the non-thermal technology like high pressure to pasteurize them to kill the bacteria. The high pressure processing basically involves application of pressure with or without external heat, so that you can make a good products. The high pressure processing commercially practiced today is essentially done at room temperature or chilled conditions, whereas you can also do pressure assisted thermal sterilization, which is essentially equivalent for canning type applications that require pressure and temperature. Now, if you look at the high pressure processing, today we talk about emerging new technology, but historically if you look at it, in 1899 there's a scientist by name Haidt in Virginia Tech Ag Experiment Station first looked at high pressure processing in a lab environment with the milk storage and other applications. So, this is kind of why the high pressure processing kind of took a longer time to get commercialized. So, I mentioned the initial applications, initial exploratory study was done in 1899, 1900. Then around 1914 with the World War I and II, I think the whole interest in the technology kind of disappeared. In 1980, Japanese looked at the world literature, then they reintroduced the high pressure processing concept into the market, and subsequently around 1985, 1990, there's a professor by name Dan Farkas at Oregon. He kind of looked at it and then he started working on it, and that's how this is reintroduced in the US, and the first pressure treated product came into the market 1997. I'm kind of giving you the history, kind of show you the nonlinear trajectory of new technology development. You know, like you probably work on it, and then if you don't see immediate market commercial application, don't worry. Eventually, if your idea is sound, this will be picked up by people and commercialized in the later stages. At the moment, FDA issued letter of no objection for two pressure assisted thermal sterilization technologies. One is potato product, another is a seafood product, but there's no commercial products available in the market, but there's a lot of interest to introduce pressure based sterilization technology. So, if you look at pressure, it is like temperature. So, pressure and temperature are part of the same thermodynamic variable. So, that means a lot of things you can do with the heat, you can also do with pressure. So, in other words, I think you can probably do more pasteurization, you can do the commercial sterilization, and you can see that the pasteurization primarily spore formers are not inactivated, whereas in the sterilization you can inactivate the spore former as well as enzymes. You can also have what they call extended shelf life food. The treatment is milder than milder than the commercial sterilization, but much stronger than the pasteurization. So, these type of processes you can do this so that you can extend the shelf life of pasteurized product, and then you also inactivate some of the weaker thermally resistant or pressure resistant spores. Beyond that, you can also see here pressure has a number of other applications. You can be able to crystallize lipids, you can be able to use the hyperbaric storage. So, in other words, imagine you have built a pressure chamber and then apply 50 megapascal or 100 megapascal and store food for months and months, similar to a refrigeration. So, you do not need refrigeration, but you can just have a pressure chamber to store the food. And you can also extract a lot of different compounds with the high pressure processing, and freezing and thawing can be accomplished. So, you can see a lot of parallels to thermal processing you can be able to accomplish. More other thing is the ultra shear technology or high pressure homogenization, which involve combination of pressure, temperature and shear, so that you can have beverages and other liquid products. In terms of high pressure pasteurized products, you can see kind of couple of broad categories: meat, seafood, fruits and vegetables, dairy based products, fed foods, like a lot of them are meat products. And what I want you to pay attention is the pressure level applied and then the target bacteria. So, if you look at the pressure level applied 500 to 600 megapascal, a chill condition for meat product, and then if you look at the control, you are targeting Listeria. Whereas, if you look at seafood, you are targeting Vibrio, and the pressure levels are 200, 300 megapascal. So, it is kind of modest pressures. If you look at E. coli, listeria in fruits and vegetables, you can probably apply again 400 to 600 megapascal pressure to inactivate them. So, the take home message is you cannot just have one target organism for entire set of products. Each product category you may have a different target organism, and then you need to make sure that you address them properly. And one other interesting thing is the pressure treatment result in extended shelf life. Compared to thermally pasteurized product, you may have 1.5 to 2 times more shelf life, and but you still need to store them in the refrigerator conditions because spores are not inactivated, and because if you have a temperature abuse, there may be spore growth that can result in outbreak. So, a lot of times when they pressure pasteurized products, especially products with the low acid conditions, they tend to acidify so that they kind of suppress the growth of the spores. At the same time, you can able to have a safe product. High pressure processing kind of has its origin in material science, material engineering type of thing, where they were using for water jet cutting, material densification, and supercritical fluid extraction, diamond making, those type of things. And you can see, for example, you can make artificial diamond at extreme pressures and temperatures, and this is a kind of commercial practice. When the food industry is kind of adapted, they were kind of trying to understand the technology from food product point of view. So that's kind of the research kind of took a while to develop, and then we can be able to get this. If you never heard about high pressure processing before, when I say 600 megapascal, how high is the pressure? If you imagine you go to the Mariana Trench at probably one of the deepest portion of the ocean, it's about 100 megapascal, whereas the pressures we are using is almost 5 to 6 times more, and the center of earth is kind of much more pressure. Nevertheless, this is a extreme pressures we are kind of using for the treatment. The next couple of slides, I am going to just go through some example commercial products, why it's commercially successful. So, the sliced deli meats, as we mentioned, it inactivate Listeria, E. coli, Salmonella, and other products, and it provides a distribution. So, why Listeria, and then why deli meat, and why high pressure processing? Around 2000, there were major outbreaks in meat products. The USDA Food Safety Inspection Service (FSIS) basically said they want have zero tolerance for Listeria in processed meat, and so they kind of provided a multiple option how meat processor can implement that. One of the options they gave was the high pressure processing, and many companies find that very practical and commercially viable. So, they introduced, since then that become much more commercially successful. So, that is around 2000. Moving forward 2025, today still high pressure processing is practiced in meat, not only for food safety reason. What they also found is, for example, in some processed meat they use nitrate, and that sometimes people worry about cancer causing issues and so on. What they found is when you do high pressure processing, they can eliminate the need for nitrate, so they have a safe product. So, that way it becomes much cleaner ingredient label, make the food safe. So, I think it's kind of liked by both the consumers as well as the food processors. And of course, you can be able to, since the introduction of high pressure processing in meat products, there were no known outbreaks in those type of processed products. Another interesting application is oysters. So, I was working in an institution in Chicago at the time. This is around 2000 time frame. So, there is a company came and talked to us about looking at technology for oysters, because oysters normally found in sea, Vibrio bacteria is a common problem, and but consumers like to eat oysters without much cooking. So, they kind of trying to find some technological solution. We were experimenting with high pressure processing at the time. What we found is, instead of going to, when we treat around 200 to 300 megapascal, take the oysters out, they even survive the pressure alive for a couple of minutes, then eventually dead. But I think that kind of proved the concept that pressure treatment can able to protect the integrity of the muscle, at the same time kill the bacteria. So, since then the seafood industry adapted oysters, and then they also adapted lobsters. And again, this is around 2005 2003 time frame. One interesting thing is, initial adaptation was on food safety reason, but today even it's successful. Part of the reason is couple of benefits from this technology. One, when you pressure treat oysters, the shell and the muscle can separate, because the shell is very rigid, the muscle is soft. So, when you are pressure treating, it detached by itself. So, the oyster industry, they call this as a shucking, and so this can be done. So, that means it's a big labor savings, and this is not previously known. So, they can able to do it, and you can see here in the lobster. So, you have a lobster with the shell, and then after high pressure treatment, the whole muscle comes out quite easily. The second thing is, when you pressure treat oysters, you can add, for example, lemon juice or some flavor agents, and they can be infused, because pressure can do mass transfer. So, you can infuse things during pressure treatment. So, that means you can create a flavored oysters and things of that nature. So, this is in this application. So, this kind of why these type of innovation, even though while it started as a food safety, then the innovation enabled them to look at broader food safety and quality benefits. The other one is this beverages. So, a lot of beverages are kind of pressure treated. For example, if you visit Starbucks in the US, the pressure treated products, the juices and things like that, they are selling. So, one interesting thing with that is that if you have orange juice and pressure treated and try to sell this as a commodity product, it may not sell well, because the cost constraints, because people kind of very sensitive to price. On the other hand, when you have some of these specialty retailers where they are selling juices good for you, health, immune protection, those type of things, consumer willing to pay, and then you can able to pay that. So, a lot of the high pressure processed products introduced in the market today, these are all more what they call premium high quality product, where consumer don't mind paying the price, but not a commodity type applications like like a standard juice or milk and things of that nature. So, that is something needs to consider. And here we can see here different type of products categories being processed in the market, and these are just examples of products available in the US. Pressure treated products are also available in Europe, Australia, China, India. So, India has a number of juices and other products in the market. Again, what I heard is that there's more and more food processors in India are interested in to get into the high pressure processing. The pressure assisted thermal sterilization or high pressure sterilization, you take the food, package it, and then you are going to preheat to certain initial temperatures, so 70 or 90 Celsius, and then you are going to pressure treat at so that the product temperature reaches 120 Celsius. So, you can inactivate spores, including the Clostridium botulinum, and you can also achieve enzyme inactivation, and you can able to achieve commercially sterile products, like for example, you can make stews, soups, coffee, tea, flavor, and many products like this. And FDA issued no objection for industrial petitions during the past 5 years. There was one in 2009, there's another one around 2014. One is mashed potato, another is what I call seafood type product. As of now, there are no commercial products in the market, but I think there's a lot of research activities going on, so that eventually you will see commercial application in the market. Now, if you are hearing about high pressure processing first time, you may ask the question, is the high pressure processing, you are talking extreme level of pressures, will this crush the food? So, for example, I have a carrot, pressure treated, is this going to smash it? I think the answer is no. The reason is there's a difference between shear pressure and high pressure. So, the high pressure, the pressure application is isostatic, so it's applied uniformly all around the product. So, to illustrate the concept, let's think about this. If you take a piece of grape and put between your fingers and you're going to squeeze them, you will see that you are going to squeeze, apply some pressure, but that pressure is a shear, so that you're going to damage the grape and it's going to burst open. On the other hand, you take the grape, maybe take a container like this, put the grape inside, fill with water, and then squeeze the container. You are going to apply isostatic pressure. The water pressure is going to transfer all around the grape. So, it's similar thing happen inside the pressure vessel. So, this is why if you look at this fruit before and after processing, they look very similar, but they are placed inside a water medium, so that they don't get crushed. On the other hand, look at this guy here. This is a styrofoam cup. It's pressure treatment, it significantly lose a lot of the volume, because all the air in the system was removed. Once the pressure removed, it cannot go back. So, as a result, if you have a leafy green, any fruits and vegetables have a lot of air packets. These are all not very good candidates for pressure treatment, but otherwise meat, seafood, almost any different varieties of food products can be pressure treated. The principle behind high pressure processing are the following: isostatic pressure. Basically, what it says is pressure is transmitted uniformly instantaneously throughout the sample, and process time is independent of sample volume. So, what that means is, if I have a small say carrot piece versus a big say chicken breast, smaller carrot piece can be cooked quite easily because it's a small size, whereas it may take longer to cook chicken or other meat products, because the size it's going to take longer to cook. Whereas in the case of high pressure processing, both going to take the same amount of time, because the pressure is applied uniformly volumetrically throughout the sample, and you can able to take it effect. The second is the Le Chatelier principle. It kind of says that any process associated with a reduction in volume is favored by increase in pressure. So, there are chemical reactions, there may be volume increase reaction, there are reactions with volume decrease reactions. So, a reduction in volume going to be favored by pressure treatment. Arrhenius relationship. So, this is one of the things scientifically pay attention. People claim high pressure processing non-thermal technology, but strictly scientifically speaking, pressure treatment is a thermal process, because you are always going to have a thermal component associated with the pressure treatment, but the extent of thermal increase is significantly low, so that you can probably ignore that thermal effect. So, that means you have to consider the Arrhenius type relationship, so that some of the thermal dependency of the reactions. The pressure treatment affect the non-covalent bonds. It has a limited effect on low molecular molecules like flavor, aroma, pigments. So, that is why pressure treatment products looks much more naturally looking, fresh, tasting type of thing. And you probably do not destroy vitamins, and it also inhibit Maillard reactions. So, there are reactions with the heat treatment, you can get a Maillard browning, those type of things, pressure treatment doesn't do that. So, in other words, if that's a desired reaction for you, you have to use heat treatment for that application. So, how the pressure treatment works? So, let us say I have want to process some vegetable cut slices or some meat products. You take them, package them, and then package that product inside a big canister. So, in other words, if you have a consumer size package, you load them in a maybe 100-liter basket, and that basket is going to be loaded inside a pressure vessel. So, you can look at the pressure vessel here. We will see a schematic come in later, but it has a pressure chamber, and then you have a closer in both sides, and then this is called yoke. So, this is kind of basically how the system looks like. Then what you are going to do is you are going to fill this with water. So, let us say that you have a 100-liter chamber, you are going to fill with water to up to 100 liters. There is no pressure change happens, but you keep pumping more and more water inside. So, maybe 200 liters, 500 liters, 600 liters, then it increases the pressure, and that is how you keep adding more and more water until it reaches 300 megapascal or 600 megapascal, and then you keep it for a certain time, and then you remove the water, and then you take the processed product out. So, one of the interesting thing is, since normally even in some of the engineering classes, we always assume water is incompressible fluid, but under these pressure conditions water is compressible. So, what that means is you take 1 liter water and you put it in the pressure machine, it is going to compress to 0.85 liters. So, that is about 15% reduction in volume, and then you are going to when you release the pressure, it goes back to the initial conditions. So, this is the schematic diagram for the equipment. It is kind of similar to what we saw, and you can see that this is the pressure vessel which is inside here, and then you are going to have the yoke which is kind of framed here, and then you are going to have the basket where loading unloading samples are here, and then you are also going to have closure. So, there is a chamber closer over there, and then you are going to have 2 pressure intensifiers, pressure pumps, and the pressure pumps use water as the pressure transfer fluid. Now, many of the lab units, pilot scale or bench scale, they use glycol or other oil type substances, and because it may be made with relatively inexpensive, whereas in the commercial industrial applications they always use water as the pressure transfer fluid. The pressure vessels, they can be made multiple ways. A simple thing is what they call a monoblock. So, this is the monoblock. You take a probably a poached cylinder, and that forms the cavity, and that you place the product inside, and then you pressure treat it. The problem is these probably going to break maybe after 1000 cycles or 2000 cycles, because you are going to develop stress cracks, and so that with the fatigue resistance and so on, you are going to break, and that is not reliable, because in food processing we do millions of cycles in an industrial level day in day out. So, that means you need a better solution. The second option is a multi-layer vessel. So, multi-layer vessel is basically you have a monoblock, and then you can add another cylinder outside of that, so that you have 2 layers. It kind of improve the fatigue resistance, but still not the ideal one. So, what is currently industry practiced is what they call wire wound technology. Wire wound technology, basically they take pre-stressed stainless steel wire, and then they kind of miles and miles of that, and then form a big cavity by winding them here, and this way they can able to stress and then release the stress, it can able to withstand those stresses even millions of cycles without any problem. So, this way this is kind of what commercially applied by all the equipment manufacturers. Then there are two types of pressurization. One is the direct pressurization, another is the external pressurization. So, the direct pressurization, imagine you have a product here and then you have a piston and then you use some type of driving mechanism to push the piston and then push, and you are going to generate pressure inside, and that causes the pressurization. And so, this is one type of application. We will see later on this concept may be used in ultra shear technology type concepts. The second is external pressurization. So, you have a prepackaged product and then you put it in the pressure chamber, and then what you are doing is you are kind of adding more water, and then it is going to increase the pressure through that way. So, this is where more commercial batch high pressure equipment employ these concepts. The yoke also made of wire wound steel and frame, and you also have to have a process control and instrumentation, because these are all very high pressures. So, they have to monitor the pressure and then able to depressurize it when there is a need, all those things. So, that is where they have to use the process automation. The pressure pump, this is just an example how a pressure pump may look like, and it comes with different horsepowers, like for example 200 horsepowers, 200 HP, 50 HP or 1000 HP, and so on, different values. And depending on how powerful your pump, you can able to achieve the pressure within that time frame. So, in other words, if I want to build the pressure in 30 seconds in a 100 liter chamber, you can do that if you use the appropriate pressure pump. On the other hand, a lot of the equipment vendors, they typically use about 2 minutes come up time for the pressure to reach 600 megapascal. So, that way they do not need to use very expensive horsepower pump, but they can use some moderate pump. And when initially started, a lot of the pressure machines were vertical orientation. What that means is they place the pressure chamber in a vertical room, and you are going to load the product inside, and then you take the product outside. It is in the same environment. And what happened is, where many processing plants, you may have constraints with the vertical space, they may not have it. The second thing is, which is more important, is the product looks very similar before after treatment. So, it is possible a lay operator who does not know much about the science can misplace the process sample to unprocessed sample, accidentally unprocessed sample get into the process sample mix. So, this way now they are using a horizontal machine, so that they have one side say raw product side, the other side you have the processed product side. So, that means the operator this side know they have to load the raw product here, the processed product there is going to be collected. So, that way they can able to operate this much more cleaner way. The commercial equipments are about 600 liter capacity, and they can probably process about 20 to 40 million pounds per year. And now, this is a new technology. So, that means the cost kind of has been coming down, but relatively still expensive. Now, this estimate may be 1 to 5 cents rather than 3 to 10 cents, but still it is relatively expensive compared to a thermally processed product. So, that means that you still cannot use high pressure for commodity type product, but you can try to use it for value added product where consumer willing to pay for it. Packaging, you had to use flexible package. So, you cannot use metal cans, you cannot use glass bottles, but you can use pouches, because remember there is a reduction, volume reduction during high pressure processing, and this allow that reduction. So, you can use different things like trays, bottles, things of that nature, but it needs to withstand the pressure and temperature, the mechanical forces encountered during processing, and then you have to use the product with the high barrier pouch. Remember, when you are processing, you are modifying the properties of the food, you are also going to modify the properties of the polymer. So, in other words, if you are familiar with the packaging science, you have probably heard the term water vapor permeability as well as the oxygen transfer values, right. So, those parameters can be affected by pressure treatment. You may start with the high barrier properties, and then after pressure treatment those barrier properties lost. So, what that means is you may start with a high value ordered product with superior quality, but you are storing the product in a package which has insignificant barrier property. So, you are going to lose your property, your quality benefits over storage. So, that is why it is always important to have proper packaging. So, this is just showing you have the oxygen transmission property for certain material, and then how the pressure treatment going to keep it without any damage. I think the figure did not come out very well. If you need, I can show you the picture. This is also published in this paper here, so you can probably get the image there. But the essential data here is pressure treatment can modify the barrier properties. So, if you have to use the proper packaging material to select the maintain the barrier properties. Let us look at the microbiological criteria. So, normally we have used thermal processing, and thermal processing we looked at the microbiology over last 150 years. So, we know how to make products safe. Now, high pressure processing use pressure. So, what type of criteria you need to establish? So, what type of pathogen do you choose? So, is pathogen in a thermal process going to be pathogen in high pressure product? In other words, let us say you are taking E. coli 0157 is one of the more resistant for heat treatment. Is that going to be more resistant for pressure treatment, or pressure treatment going to be easily inactivate them? So, those are the type of things. So, what you need to do is kind of first look at the most resistant pathogen of public concern survive the process. So, if you are processing meat products, what are the outbreaks? So, is that E. coli outbreak, or is it Listeria caused the outbreak, or is the Clostridium caused the outbreak? So, you kind of gather that information and then see how much inactivation you need, and you also need to consider the injury and recovery. Remember, pressure treatment is a relatively milder form of treatment. So, that means bacteria may appear dead, but they are really injured. So, with the right growth media they will come back, and a lot of times food is a good nutrition medium. So, they may grow back. So, you have to consider that as well. And then you also need to consider the protective effect of composition, pH, water activity, similar to what we talked earlier, and then you have to validate the process. So, again, if you are a student of microbiology, you know that there is no one single Listeria, there may be thousands of Listeria there. So, somebody has done a study where they looked at 100 different type of Listeria, and what they found is some strains they had 0 log reduction, some strains they had 6.75 log reduction, some strains they had probably about 3 log reduction. Now, imagine yourself as the manager who needs to decide the safety of high pressure processing. Which one of the strains do you choose? I will give you 3 choices: 1, 2, 3. Do you choose 1? You probably do not choose 1 because there is no log reduction. So, if you choose that, you are going to say high pressure is not commercially viable, but millions of products are commercially processed. So, how do they manage to do that? If you choose 3, you are going to say I am going to get log reduction, 6.75 log reduction, but you may have a lot of more resistant spores or bacteria survive, so you may get outbreak. So, the point of the matter is you do not take number 2 either. So, what you have to do is, let us say you have a high pressure processing plant in say Ranchi, then you look at in the neighboring states, and let us suppose you are processing vegetable products. So, you can say, okay, over the last 50 years, 100 years, what type of outbreak happened in vegetable products in around this place where I am going to get my raw material, what type of pathogens there, and then you take those pathogens and do the study, make sure you can inactivate them. Because one of the common mistake people do is they look at the published literature and then they try to mimic that for their process, but that may not guarantee the safety, because the published literature may be different resistant than the bacteria found in your area. So, you have to kind of pay attention, and this is I am illustrating with the high pressure processing, but this may be true for many non-thermal technologies like pulse electric, UV and other processing technologies. Another thing you need to consider, when you apply high pressure, there is going to be some temperature increase. So, that means you are going to have apply both temperature and pressure during treatment. So, how do you consider that? So, in this study we looked at a chemical marker called M2 marker with a whey protein gel, and first we did this heat treatment 105 Celsius and say about 5 minutes, and then you can see that the marker yield increased with increase in holding time. So, this is primarily heat treatment. The next we have done is pressure treatment at 30 Celsius. You can see that the same gel, you do not have formal pressure treatment, because pressure kind of inhibit that reaction. So, you have decrease. When you have 700 megapascal, slightly similar thing. What if I increase the temperature to 105 degrees Celsius? You can see that marker yield is increasing. So, in other words, you have two forces acting on it. One is the heat, which probably in this case favor the reaction formation of the chemical. The other is pressure, which is antagonistic. So, it is kind of inhibit the formation. What you see is the net result of that. So, when you do high pressure processing, especially with the combination of high pressure and temperature, you have to consider both thermal effect as well as the pressure effect. So, to illustrate the point, we looked at the Bacillus cereus spores in cooked rice, and you can see that when I have just the thermal process at 85 degrees Celsius, it takes almost 160 minutes. It is almost like 3 hours to get certain log reduction. So, 7-8 log reduction. But if you are doing only 60 Celsius, you can achieve the same in about 7 minutes, or if you go to 85 degrees Celsius, you can even achieve in about 4 minutes. So, you can see that pressure and temperature can synergistically inactivate the bacteria as well as some of the other chemical compounds. Here we are looking at the inactivation of one of the pressure resistant spores called Bacillus amyloliquefaciens. So, it is one of the pressure resistant spores, and the point I am trying to make here is you have the log reduction versus temperature, the log reduction versus pressure. What you see here is at 0.1 megapascal at a lower temperatures, you can see that the log D values are much higher, whereas for pressure treatment these are much lower. So, this means there is an enhanced pressure lethality, whereas as you increase the temperature at 120 degrees C, they kind of clump together. So, that means pressure, if you operate the pressure vessel at 120 Celsius, it becomes like an expensive autoclave, because there is no contribution of pressure lethality, it is primarily coming from heat. Temperature become dominant factor. So, then we kind of went and did a mathematical model where we looked at the D and Z values for the bacteria from pressure treatment We also looked at the D and Z value for the bacteria for the thermal processing, and then we integrate them. And let me kind of explain here. So, this is 600 megapascal, 103 Celsius for 5 minutes. So, this is thermal only lethality, whereas this is kind of combined pressure and thermal lethality. You can see that at that conditions you have a more lethal effect due to pressure and temperature, almost negligible effect only with the heat. Now, if you go to increase the temperature to 600 megapascal, 116 Celsius, you can see this is the pressure thermal lethality, this is thermal only lethality. So, they are kind of coming close together. If I do this at 121 Celsius, you can see that those two will become same. So, because the temperature lethality become a dominant factor, pressure does not have any lethal effect. So, you have to kind of consider some of those things together. In terms of shelf life, high pressure processing extend the shelf life. So, for example, if you have orange juice 8 days versus 120 days, if you have hummus about 80 days, salsa 15 versus 120 days. So, you can see that quite significant extent of shelf life. From a consumer point of view, they may not find this benefit, because sometimes consumer expect things to spoil in couple of weeks in the refrigeration, but it gives the opportunity for food processor to distribute for longer distance. So, for example, you make hummus in say Cuttack, you can probably send to, for example, south of Kerala or Kashmir, or you can probably export to Europe or US and so on, because that kind of provides the longer shelf life, help you to send to a wide geographical distances. Enzyme inactivation, as mentioned, pressure is not very good with the enzymes. The efficacy varies based on the type of enzyme, pressure level, time, pH, temperature. So, a simple solution is, if you want to pasteurize product with high pressure, you do thermal blanching followed by high pressure processing. That way it takes care of the enzyme with heat, and then you take care of the microbes with the pressure treatment. Now, some nutritional things here. Pressure is also helpful to protect ascorbic acid. So, here you can see that pressure treatment with ascorbic acid, it kind of retained everything together. On the other hand, if you look at thermal processing at a different temperature, you can see a degradation with a certain time, and then if you have a combination of pressure and temperature, you still have a degradation of ascorbic acid. So, in other words, pressure treatment at chilled condition reasonably or mostly protect most of the nutrients. On the other hand, when you start adding heat to it, it is going to probably degrade to the extent how much heat you are adding to the system. This is just to look at the furan formation, because there is a concern with high temperature furan can be formed, and that can be a healthy concern. So, we kind of looked at thermal processing, and then PATP is pressure assisted thermal processing, HPP high pressure processing. What you see here is the heat always going to form some furan in different type of juices. On the other hand, the HPP, it kind of forms below detection level. Now, I think I also want to acknowledge that even though these levels shown here are high, but from a regulatory point of view, they are still within the threshold, so that they are safe to consume. But nevertheless, with the increased detection efficiency of various analytical techniques, sometimes consumers want to know what compounds formed, how they can be controlled during processing, and so on. So, this is kind of provide pressure temperature history during high pressure processing. So, for example, you may have a product at certain initial temperature, and then you kind of equilibrate it. and then you're going to load inside the pressure vessel, and then you're building the pressure, and then you're holding the pressure, and then you're going to depressurize it. So, during the time you can see that there is a temperature increase, and then it is maintained, and then when you remove the pressure, the temperature falls down. So, what is happening here? So, remember I talked earlier, when you are compressing the material, the liquid is going to compress, or even the substance is going to compress 10-15%. So, when you compress the material together, the molecules coming together, that means they have increased opportunity for friction, and that friction shows us the temperature during pressure treatment. And then it is maintained as long as you maintain the pressure. When you remove the pressure, then the molecules, the substance go back to its original volume. So, that means no longer they have opportunity for increased friction. So, the temperatures kind of goes back. So, this kind of is called heat of compression, and we have kind of determined the heat of compression for different substances. So, to illustrate the point, we have done some experiments where we looked at water, skim milk, vegetable oil, and different products. And you are treating 300 megapascal 25 degrees Celsius. So, this is 25 degrees Celsius, 300 megapascal. You increase the temperature, it kind of comes down. So, you can see the temperature increase is about maybe 12 degrees Celsius. Look at vegetable oil. You can see that it starts 25 degrees Celsius, it goes close to 47 Celsius. So, what happened? Both water, milk, everything start at same temperature, but why oil kind of goes much higher temperature? The reason depends on the polarity. If you look at water, these are polar molecules, that means these are oily compact molecules. So, when you compress, you can compress only so much, whereas if you look at lipids, they are non-polar, long chain molecules or short chain molecules. So, that means you compress, they are going to compress certain way, give out some heat, and then try to be stabilized there, and then you further compress, it is going to keep compressing, and each time it is going to give out some heat. So, that is why there is a significant temperature increase during the fats and oil. So, as a result, you can able to document the temperature increase depending on different substances as well as the initial temperature. Normally, in the literature used here, there is a 3 degree temperature increase per 100 megapascal pressure, that is done at 25 degrees Celsius, whereas if you do chill condition, the temperature increase even less, it is about 1 degree Celsius, whereas if you have a 70 degrees Celsius, you may get about 5 or 6 degrees temperature increase in water. And if you look at fats and oil, they have about the 6 to 9 degree temperature increase under these conditions. You also need to pay attention to the technology limitations because non-thermal technology like high pressure do not inactivate spore. So, you have to combine with heat to make them safe, and when the water activity is very low, high pressure is not good. It requires some water, so that it is effective against the bacteria. And if you have air packets, again it is not good with the pressure treatment as well as PEF. It kind of provides look at this. And when you have light based technologies, you have to consider the shadowing, and many of the non-thermal technologies, they have a high cost of equipment. So, that is something needs to consider. And one of the limitation of non-thermal technologies, or at least it is not thoroughly researched, because today there is also a lot of concern about presence of heavy metals, pesticide residues in fruits and vegetables and products. Pressure treatment is effective in inactivating bacteria, but not necessarily their efficacy against the heavy metals and pesticide residue is not known. So, that needs to be looked at in the future. Other interesting thing is in the US, with the success of high pressure treatment, there were a lot of copycats. What that means is, for example, like high pressure processing, people selling juices. So instead of subjecting them to 600 megapascal pressure, they were subjecting them, 600 megapascal pressure is about 87,000 pounds per square inch, but they were applying 100 psi pressure or 200 psi pressure. So this is like a juice pressing equipment, and then they were selling this as a high pressure processed juice. From a consumer point of view, they do not know what's the difference between pressing the juice or subjecting to high pressure processing. So the industry then formed a logo, so that they said anybody who is properly treating high pressure with certain proper conditions, they can use the logo. Anybody just using only 50, 10 psi, 100 psi type of thing, they probably may not able to use this logo. So this way they kind of try to build a safety mechanism against people trying to make money quickly without doing the proper scientific work. So take home message is, pressure is a fundamental thermodynamic variable. It has a very versatile applications. We initially pressure started as a food safety technology. Today it's used in wide range of applications, and in addition to pressure treatment in food applications, it has applications in cosmetic, pharmaceutical and medicine, because for example, you can create vaccines, or you can develop some novel cosmetic from food ingredients with these type of things. Now, I am going to talk in the next couple of slides ultra shear technology, which is basically a continuous version of high pressure processing. Remember, food industry always interested in continuous version of the technology rather than the batch version, so that it helps to improve the productivity, and this is where the high pressure processing come in. So the concept simply illustrated here. You have a raw juice here, and it's sent to a pressure chamber treated 400 megapascal. So remember here, the juice is not packaged, it's just the whole liquid is here, and then you are going to discharge through a shear valve, so that the pressure is relieved, and then the product comes out here as a treated product. How it works in a pilot unit here. So you have a treated product, and the product is pumped inside the flexible tubing. So what this vision has done is, they put two flexible tubing inside the pressure chamber. So the product stays inside here. The pressure transfer fluid is kind of passed through the annular space. So they squeeze the tube, pressurize, and then when you remove the pressure, it kind of retains. So after you remove the pressure, it goes through a shear valve where the pressure is discharged, and then it goes through a holding tube, cooling heat exchanger, and then aseptic filling. If you look at this section, you probably see the holding tube, cooling section, and then aseptic packaging. You probably see them in the aseptic processing as well. So essentially, ultra shear technology kind of merges pressure technology, which is a non-thermal, to the pressure thermal based technology. So it's a hybrid thermal non-thermal technology. So this can help with the making clean label dairy, plant protein beverages. It can also use as a green extraction technology. It has applications in variety of industries as well. So the thermal part comes after it passed through the shear valve. So when the product comes out the shear valve, there is a significant temperature increase. There is a 20 Celsius temperature increase for 100 megapascal. So if you apply 400 megapascal, you are going to have 80 Celsius temperature increase. So then you have a whole tube, and then you have the cooling section, and so on. So I will come to that in the next couple of slides. So pressure comes in, you pressurize it, then you are getting into the pressure, they depressurize it, and when you depressurize, there is a significant temperature increase. Then the sample can be considered as a thermally processed sample, and then the existing thermal process regulation potentially used to may demonstrate the safety. So, the level of shear happening during the high pressure shear is about 10 power 7. So, normally in the standard shear it may be 10 power 2, 10 power 3, here it is 10 power 7. So, that is why there is a significant temperature increase happening. So, to illustrate the point, here there is a temperature increase 3 Celsius per 100 megapascal during isostatic pressure processing. So, this temperature increase we are going to go back when you remove the pressure, whereas you can see here 18 degrees temperature increase per 100 megapascal during ultra shear technology. This is permanent, that means you have to use external cooling to remove that heat. So, that is kind of the two difference between the batch high pressure processing, also the high pressure homogenization, and the process. So, let me kind of try to come here. So, what we have done is we use this concept to pasteurize or sterilize products. Let us suppose I take a juice, I process with 5 degrees Celsius initial temperature, and let us say I treat 400 Celsius, and so that means 5. Let us, for the purpose of calculation, I am going to make this as 400 times 18 by 100. So, 5 plus, so approximately 77 Celsius. So, you can see this is kind of similar to pasteurization temperature, and you can probably use existing pasteurization temperature to get this passed through the regulatory authority, because in the holding tube the product going to spend enough time what you have in thermally pasteurized product. Now, if you look at other side, let us suppose I take 75 degrees Celsius initial temperature of my product. So, that means I have to heat my product, then I am applying 400 megapascal pressure, and then again this 18 degrees Celsius temperature increase. So, 147. So, you can see that this is kind of getting in the neighborhood of USG treatment of milk or any products. So, that means you can do USG, make a self-stable product under this condition. So, simply manipulating the initial temperature and the applied pressure, proper shear valve, you can pasteurize or sterilize food products using this approach. One of the interesting thing with the ultra shear technology is that it kind of shifts the particle size much shorter, lower end compared to the regular thing. So, you can see the untreated milk is probably somewhere this blue line here, whereas high pressure processing also somewhere in this cluster, whereas the ultra shear technology shift quite a bit in the lower end. So, you can able to have much finer particles. And this is a particle shift in tomato juice. So, you can see that control versus the USG, control versus thermal processing, control versus HPP. So, essentially control, thermal processing, HPP, they have a similar, whereas USG shift the particle towards the lower end. And what we found also, depending on the type of material, the shift probably not going to be infinite. So, maybe up to 160 megapascal there is a decrease in particle size, then you are going to start aggregating. So, what we found is you may have to add a secondary shear valve, so that you can remove that, so that you can still maintain the particle size. Another interesting thing is pressure temperature can combine, so that it can significantly modify the rheological properties. I know it is a busy slide, but let me kind of try to convey here. We took milk, pea protein, and then we had different combinations, like for example 1:0.5, 1:3, and then we were treating with pressure, high pressure, ultra shear technology, and then we are also doing traditional homogenization, which is like 3000 psi. What we found is normally pressure treatment, thermal processing, the particle size doesn't the viscosity doesn't significantly increase. This is the traditional homogenization, whereas you can see here this is the ultra shear technology. It's significantly increased. What that means is you can start with a liquid, say milk and pea protein beverage, and then by proper conditions of pressure, temperature, you can have a beverage, the output may be a liquid, or you can have a sauce, you may have a thickened beverage type thing, or you can have a gel which is much more thicker. So, it can modify the viscosity properties quite a bit. So, it kind of creates a lot of new structural applications with various food processing applications with this ultra shear technology. And you can see that how the particle size can be significantly reduced. You can see the untreated particles, raw milk and protein versus the UST treatment, whereas if you have a cream and pea protein, you can see much thicker gel can be created. One of the questions we always had is, you had different non-thermal technologies. The industry always asks us, which one do you choose? I think some of you asked the question, which technology to choose, and the answer is it depends on various factors. But from a nutrition point of view, we wanted to see how different non-thermal technologies affect the nutrition. So, we took beetroot juice, and then we thermally process them, high pressure process them, ultra shear technology process them, and then use the NMR to analyze different components present in this. So, you can see lectin, there are different components, valine, glutamine, alanine, and so on. So, there are so many different things the NMR can differentiate. And then you can see this is the unprocessed sample, and you can able to separate different treatments. So, I believe this is the this is the this is the HPP. You can see it's relatively close to thermal, and then thermal had more degradation, and then ultra shear technology has the next more degradation. So, in other words, if you look at batch high pressure processing, it's primarily thermal processing. So, so you have thermal processing kind of degrade more nutrients, whereas ultra shear technology has less degradation, and then the pressure treatment has the least. And you can see that sensitivity changes for different things. So, here heat destroy more of them, whereas HPP and USG retain more. So, in other words, you can also now have another tool where you can probably look at the metabolomic analysis as well as the microbiological analysis. Then you can get a comprehensive picture. What is the impact on my microorganisms? What is the impact on my nutrients? So, this is more shear sensitive product. So, I may use this technology, whereas this is more heat sensitive product, I may use this technology, and so on. So, you can kind of, rather than blindly selecting technology, you can probably try to build in some scientific rationale behind your choice. So, ultra shear technology is an hybrid technology which combines pressure and non-thermal, and there are variety of clean labeled beverages can be processed, emulsions can be created, because you have a significant particle size reduction, rheological characteristics and stability all there, and then you are going to have diverse product applications. At the moment, the technology is not commercial, but I think in the coming years we expect the technology to get this commercial. At the moment, we have some companies working to commercialize certain nano emulsion type products. So, here are some selected readings.
Good morning. I wanted to know currently what your lab is, what is the focus of your lab right now with high pressure processing? What are they working on right now?
So, one of the things right now we are looking at is we are looking at different technologies, how that affects the nutrition. So, I think so I saw show the results from beetroot, but since then we were processing number of other fruit juices, and then we were comparing how different technologies, thermal, ultra shear technology, and HPP affect the degradation of the nutrients. So, a little bit focus on metabolomics, but a lot of those things are driven by industrial interests and applications. So, there is also interest in PATP, pressure assisted thermal processing as well. So,
Sure. So, what are the parameters that are being monitored when these technologies are put to use? Like when a product is getting high pressure, what are the parameters that are
right,
being
sure. So, for high pressure pasteurization, pressure, temperature, and time, these are the three parameters. So, in other words, normally I keep saying pressure, temperature, and time. Now we add high pressure, temperature, and time. Even though the industry get around temperature by putting the pressure vessel inside a refrigerator space. So, when you have a refrigerator space, you do not need to monitor, control the temperature. You just only focus on monitoring the high pressure and processing time.
Sure. What I was trying to ask is that the quality of the product. What are the product qualities that are being monitored while the product is going through high pressure processing?
So, after high pressure processing,
Yes.
the product is evaluated same as anything we do not today in food science or thermal processing of products, right. You look at the texture, look at the color, you look at the nutrition, look at the microbiological safety, whatever normally you do, you probably take care of those things.
Sir, I have only two technical questions. Since in case of like proteins, sulfur containing amino acid and aromatic amino acid, that can be easily oxidized. Can you give any idea how it will behave when HPP will be applied?
So, what type of product?
And in protein, there is a mostly aromatic amino acid groups and sulfur containing amino acid. If we use any technology, these are the most sensitive amino acids. It can be easily oxidized, degrade, into convert into any other form. Can you have any idea how it will behave when we applied HPP?
Yeah, I do not know the specific compounds. So, probably I have to look at the literature, somebody has done it, or new studies needs to be performed.
And second one is, you told us like HPP reduce the particle size. In large scale operation,
not HPP, the ultra shear technology.
Okay, sir, yes. So, why not they are using ultrasonication? It is mostly effective to reduce the particle size.
Right. So, remember there is no comparison between technologies. Yeah. Each you have different tools. It is up to the process to use the different tools, right. So, each one has a unique strength and weakness. Then some products may be helpful for certain things, some help the others, and so on. So, like if you look at ultra shear technology, PEF, UV, so these are all can be used with the liquid products, and you can also use the Omi heating for in terms of pasteurization, sterilization. So, you have a gamut of tools available. Which one do you need to use for a specific thing? I think it's up to the food processor, their goals and their resource availability, all those things.
Sir, to prevent the aggregation, is the industry people adding any additives to prevent the aggregate of the particles? Since ultrasound technology reduce the particle, it has a tendency to agglomerate together. Maybe if so, is there any kind of additive they are commercially available that can be used to prevent this agglomeration?
So, again, what we are reporting is a research results. So, it is not industrially practiced, that is number one. So, the goal at the time was look at clean label. So, what we are trying to do is we are not trying to do anything additives, we want to do everything only with processing. So that means pressure, temperature, shear. So we are not adding any additives, any of those things. Now, when it goes to industrial practice, I'm sure they're probably going to use a combination of processing and additives so that they can probably achieve. And some of the additives potentially could be more natural additives rather than synthetic additives, so that they can maintain the clean label type status.
Okay, thank you, sir.